Have you ever wondered about the smallest particles in the universe and their strange behavior? Welcome to the intriguing realm of quantum physics, a theory that seeks to explain the behavior of particles at the atomic and subatomic levels. Born in the early 20th century, quantum physics was a revolutionary idea that challenged the very foundations of classical physics. It was a time when scientists like Max Planck and Albert Einstein began to question the conventional understanding of the physical world. Max Planck, often called the father of quantum theory, introduced the concept of energy quantization, while Albert Einstein, in his celebrated photoelectric effect paper, proposed that light could behave as both a wave and a particle. Their groundbreaking work, along with contributions from many others, laid the groundwork for what we now know as quantum physics. So buckle up, as we're about to embark on a journey that transcends the boundaries of the visible universe. Now prepare to dive into the fascinating world of quantum physics. Imagine being in two places at the same time. Sounds impossible, right? Not in the quantum world. Welcome to the mind-bending reality of quantum superposition, a concept that makes the impossible possible. In the realm of tiny particles, things don't behave as we'd expect. You see, in this quantum domain, particles can exist in multiple states at once until they're measured. Think of it like this. Imagine you're flipping a coin. In our everyday world, that coin is either heads or tails. But in the quantum world, it's as if that coin is both heads and tails at the same time, until you catch it and look at it. That's quantum superposition. To better explain this, let's delve into the infamous thought experiment by physicist Erwin Schrödinger, known as Schrödinger's cat. He proposed a scenario where a cat is placed in a sealed box with a tiny bit of radioactive substance, a Geiger counter, a vial of poison, and a hammer. If an atom of the substance decays, the Geiger counter detects it and triggers the hammer to smash the vial, releasing the poison and killing the cat. If no atom decays, the cat lives. Now, according to quantum mechanics, the radioactive substance is in a superposition of decayed and not decayed states. So by extension, the cat is also in a superposition of alive and dead states. It's only when we open the box and observe the cat that this superposition collapses into one of the possible outcomes, a living cat or a deceased one. In essence, the cat is both alive and dead until we open the box. This might seem utterly bizarre, but that's quantum mechanics for you. It challenges our everyday perceptions and takes us into a world where the conventional rules of physics are turned on their head. In the quantum world, the cat is both alive and dead until you open the box. What if I told you two particles can instantly affect each other, no matter how far apart they are? Welcome to the mind-boggling world of quantum entanglement. It's an idea so strange that even Albert Einstein dubbed it spooky action at a distance. Yet it's a fundamental part of quantum physics. Imagine two particles. Let's call them Alice and Bob. These particles are born together, they're entangled. This means that the state of one is instantaneously connected to the state of the other, regardless of the distance between them. No matter if they're a room apart, a city apart, or even galaxies apart, they're still connected. Now let's say Alice decides to spin up. Well, Bob, even light years away, will instantly start to spin down. It's as though Alice sent Bob an instantaneous message faster than the speed of light, telling him to change his state. But remember, nothing physical is traveling between Alice and Bob. This isn't a message in the traditional sense, it's quantum entanglement. You might be thinking, wait, doesn't this violate Einstein's theory of relativity, which states nothing can travel faster than light? Well, in a way, yes. But it's not that simple. Quantum entanglement doesn't involve any transfer of physical stuff or information. It's more like Alice and Bob are two sides of the same coin. It's a concept that baffles even the brightest minds. Some argue that entanglement suggests the existence of higher dimensions we can't perceive, while others believe it hints at a deeply interconnected universe. Despite its mystery, quantum entanglement holds immense potential. It's the backbone of quantum computing, the technology that could revolutionize our world. It's also the principle behind quantum teleportation, which might one day allow us to transmit information instantaneously across vast distances. Quantum entanglement is a paradox, a mystery, a magic trick performed by the universe itself. It defies our everyday logic, challenges our understanding of reality, and yet, It's a fundamental component of the quantum world. It's like magic, but it's actually quantum entanglement. Imagine being able to walk through walls. That's everyday life for a quantum particle. Now we're diving into the surreal world of quantum tunneling. This is where quantum particles pull off their most incredible stunts, defying the constraints of classical physics. Quantum tunneling is like the ultimate magic trick, where particles pass through barriers as if they were mere illusions. Let's break it down. We're all familiar with the laws of classical physics, right? A ball can't roll uphill without a push. A car can't pass through a wall. These are the rules we live by in our everyday world. But in the quantum realm, these rules are more suggestions than hard laws. In the quantum world, particles like electrons can be in multiple places at once. They exist as a wave of probabilities rather than a definite entity in a specific location. This wave can extend beyond physical barriers such as walls. So an electron could be on one side of a barrier and then suddenly appear on the other side without ever having passed through the barrier itself. This is quantum tunneling. This isn't some form of teleportation, though. It's a result of the fundamental uncertainty that rules the quantum world. You see, an electron doesn't move from point A to point B like a car driving down a road. Instead, it exists in a state of flux, with a certain probability of being found at any given location. Now, you might think, surely the probabilities drop to zero inside a barrier, right? But that's not the case. There's always a tiny probability that the electron can be found on the other side of the barrier. And sometimes when we're not looking, that's exactly where it ends up. Quantum tunneling isn't just a theoretical concept. It's a real phenomenon that plays a key role in many aspects of our world, from the nuclear reactions that fuel the sun to the transistors that power our computers. So next time you're locked out, just wish you were a quantum particle. Scene script. Can you be certain about anything? In the quantum world, even certainty is uncertain. Let's dive into the world of the uncertainty principle, a concept that is as fascinating as it is perplexing. This principle was first formulated by a German physicist named Werner Heisenberg back in the early 20th century. Heisenberg's uncertainty principle is a fundamental concept in quantum mechanics, and it states that you can never simultaneously know the exact position and momentum of a particle. To put it simply, the more precisely we measure one value, the less precisely we can know the other. Imagine you're trying to measure the position of a quantum particle. As you zero in on its location with greater precision, you'll notice that its momentum, which is a product of its mass and speed, becomes progressively more uncertain. The same holds true if you're trying to measure its momentum. The more accurately you determine its momentum, the fuzzier its position gets. But why does this happen? Well, it's not because of any limitations in our measurement tools or techniques. It's a fundamental aspect of the quantum world. The uncertainty principle is not about what we can know, but rather about what nature allows us to know. It's a property inherent to the quantum world. It's like trying to catch a slippery eel in a dark pond. The more you focus on where it is, the harder it becomes to predict where it's going, and if you focus on where it's going, you lose track of where it is. This principle has profound implications, and it challenges our everyday experiences. In our everyday world, we're used to knowing both where things are and how fast they're going. But in the quantum world, things don't work that way. The quantum world follows its own set of rules, and the uncertainty principle is one of them. The more you know about a quantum particle's position, the less you know about its momentum, and vice versa. That's the uncertainty principle for you, a cornerstone of quantum mechanics, a testament to the intriguing and mind-boggling nature of our universe. So what do we know about the quantum world? It's weird, wonderful, and completely unlike anything we're used to. In this deep dive, we've grappled with some of the core concepts that make quantum physics truly fascinating. We've seen how superposition allows particles to exist in multiple states at once, a concept so counterintuitive it makes our regular understanding of the world seem almost quaint. We've looked at quantum entanglement, where particles, no matter how far apart, remain inexplicably linked, behaving as if they're in two places at once. We've explored quantum tunneling, where particles can pass through barriers as if they were mere illusions. And lastly, we've delved into the uncertainty principle, where the more precisely one property of a particle is known, the less precisely the other can be known. It's a world where certainty gives way to probabilities. Remember, in the quantum world, the impossible becomes possible.